Okay, I will start a minute early. So, today we are going to define the notion of the adjoint of a linear map acting on a vector space with an inner product. Okay, so let V be an n-dimensional real vector space endowed with an inner product. We will now define, we will show first that for any linear map A hat B to V, there exists, let me say, given any unique A hat dagger, this thing is called dagger, which also maps V to V, and it's linear, characterized by the property that given any vector V in the following property, given V, W in V, AB inner product W is A dagger W inner product V. So, and the association A going to A dagger is a linear isomorphism LBV to LBV. Okay, so before I let me just complete this definition. A dagger is said to be the adjoint of A. I should remember to put hats because I'm not talking about matrices, but of linear maps. So I want to define the adjoint of a linear map from V to V, given that V has an inner product. And to define that, I need this following result, which is the underlying thing. Given any linear map A to V, there exists a unique linear map A dagger characterized by this property. For any pair of vectors V and W, the scalar product of W with A hat acting on V is equal to the scalar product of A dagger V W with V. Okay. So there are two things in this claim. First of all, there exists and there is a unique. Okay. So I have to, so once I show that there exists such an A dagger and it's unique, I can call it the adjoint of A. And then once it's unique, the fact that this A going to A dagger is linear in A is easy to see. Okay, So
sir,
okay.
this
Yeah.
above condition will be true for any V and W in V. I mean, for the definition.
Yeah, for that's given any V and W in V. That's given V, W, and V. Okay.
Oh,
if you
okay.
want to be given any V and W, this should be true.
Okay.
Take any pair of vectors V and W, this should be true. That is the definition of A dagger. First of all, so before I prove this, are there any questions about the statement? I'm making a claim associated to any, provided that I have an inner product on V, I can define A dagger for any A. For any A hat, I can define an A hat dagger. And such that this equation is satisfied. That is a claim. I have not proved it. Can I go ahead with the proof? Hello? Can I go ahead with the proof? Or do you guys want to some time to stare at what I have written to digest it? Hello? I can't hear you. Yeah.
So I had a question.
Yeah.
What exactly do we mean by the association A to A adjoint? Like what?
So the
what
map. So for every A, there is I should call it this map. Which so consider this map from L. Do you understand the notation LVV?
Yes, yes, I got
that. So now once you accept the claim, for every A hat, I'm associating an A hat dagger. Now, LVV, we've said several times, is a vector space. And my point here is that this is a linear map from LVV to itself, and it's an isomorphism.
Okay, got it.
Yeah, yeah, thank you. Okay, so I'm going to give a, so because of shortage of time, I'm not going to give the most natural proof. I'm going to give a proof that uses matrices. So this is going to be an unfortunate fact because we are running out of time. So I have to give not that the proof is difficult or long, but it's slightly unnatural. The natural proof would not go via matrices, but I'm giving you an unnatural proof, okay? So proof of the claim. So what is a claim? So since I have not labeled this clearly as a claim. So what we will show, so I will change that to claim. Okay. So now I'm going to prove the claim. First, suppose V is Rn and the inner product is the standard one. Then let us check that if we define A hat as follows, A hat dagger as follows, the equation, so let me call this equation star, is satisfied. Okay, so I'm going to define A hat dagger as follows. Start with A hat. It is given by a matrix A, and take the transpose of the matrix, okay, and then define A hat dagger is the linear map corresponding to A transpose. Okay, so I claim that if you define A hat dagger like this, then in fact, this equation star is satisfied for the standard inner product. So let us check that. WAB is sum over I, WI, ABI, I equal to 1 to n, because it's the standard inner product on Rn. The standard inner product of this vector and this vector is got by taking the ith component of this vector, the ith component of this vector, multiplying them together and summing over I running from 1 to n. Okay, I am again forgetting hats everywhere, so let me be clear about putting hats. But the matrix of A, the matrix A is defined such that A hat VI is AIJ Vj, sum over J. So A hat Vi is sum over J, Aij Vj. This is the association. This is the how the matrix Aij A is defined. Capital A is defined. Okay. So this is equal to sum over I equal to 1 to n, sum over J equal to 1 to n, omega I Aij Vj. On the other hand, if I define A dagger as above, A hat, sorry. By the same, again, we are working with the standard inner product on Rn. This is sum over I equal to 1 to n. A hat dagger Ij Wj Bi sum over J. But the way we defined A hat dagger, its ijth component is entry is A Ji Wj Vi. Now exchange orders of of summation, and you get 1 to n, sigma I equal to 1 to n. No, don't do that. Interchange the indices I and j. So this is sigma j equal to 1 to n, sigma I equal to 1 to n, Aij Wi Bj, which is now I equal to 1 to n, sigma j equal to 1 to n, omega I Aij Vj. Now compare with this. If you compare this expression and this expression, you see that they are the same. So I have gone a bit quickly here, but this is a computation that you should do on your own. So this shows that defining a dagger as above works for the standard inner product on Rn. Okay, so in other words, the operation on matrices that you are familiar with, taking an n by n matrix and taking its transpose, has the property for the standard inner product on Rn that the corresponding linear maps. So in other words, A transpose corresponds to A hat going to A hat dagger. Yeah, Srijan is asked, is A dagger unique? Because that was claimed. Part of the claim was that there is a unique A dagger that will do the job. Okay, I have not proved that. So far, I only proved that. Okay, let's summarize. What? Okay. So start with, we have proved that given linear map A dagger Rn to Rn, the linear map A dagger defined by the transpose of the matrix A corresponding to A dagger to A hat has the property A dagger W D is W A D for the standard inner product for every W V in Rn. Okay, that is what the above computation shows. Okay, so at least for the standard inner product of Rn, there exists a map that associates to every A dagger, and this is also clear, by the way, that this is a linear map, because taking the transpose of a matrix is linear, and going from linear map to matrix is a linear map from LBV to n by n matrices. So the association A to A dagger is linear, and if I repeat it twice on the metric side, it corresponds to taking a transpose of a matrix and taking transpose again. So I'm saying it's clear, but you have to check that A hat going to A hat dagger by the above prescription is linear. Also, A hat dagger is A hat, because on the metric side, it is taking the transpose of a matrix and then taking its transpose again, which will bring you back to the original matrix. So taking this dagger twice is the identity map LBV to V. So this shows that at least this map is an isomorphism. The only thing I have not shown is that there is no other way of defining a hat dagger. Okay, so that is a uniqueness part, which somebody asked, is it true? It is true, but I have not proved it. but I'm leaving it as an exercise. So uniqueness of A hat dagger given A is left as an exercise. Or you can look at the notes where I actually prove everything carefully. Okay. Now, so far so good for in the case when V is Rn and you have the standard inner product on Rn. But supposing V is just some n-dimensional real vector space and I'm just given some inner product, what can I do? How can I prove this claim for a general n-dimensional real inner product space? What can I do? Any ideas? We can use something that we proved in the last lecture. No ideas?
Sir, this is not really a fleshed out idea at all, but from something I was reading, I vaguely recall something about the dot product being one of the only ways to define an inner product.
Yes.
And
so in fact, so that is essentially what we proved in the last lecture. We proved that given any inner product vector space, there exists an orthonormal basis. Okay. So you can do the following: take a hat, choose an orthonormal basis, take the matrix of a hat with respect to that orthonormal basis, take the transpose of that matrix and define the corresponding linear map to be a hat dagger and show that this does the job by exactly the same computations as above. Okay.
Okay, I think I'm seeing it. So.
That amounts to what you said. Okay. So I will just write down what I said in speech. So for general inner product space, V with dim V equal to N, choose an orthonormal basis U1, UN, given A hat V to V, let A be the matrix of A hat with respect to U1, UN. Define A hat dagger by demanding that the matrix of A hat dagger is A transpose. Check that with this definition, A hat dagger WV is W A hat V for every V W in V. So the important thing is this will work only if you do this with respect to an orthonormal basis corresponding to the inner product. And what we've seen is that given any real inner vector space, inner product space, by starting with any basis and doing the Gram-Schmidt orthogonalization, you can get an inner product. Okay. So this also I leave for you to check.
So what is written in the second line? Define A dagger something.
Yeah, define A hat dagger by demanding that the matrix of A hat dagger is A transpose.
Okay, thanks.
Okay.
Yeah, fine.
Yeah. So the point is, so as I have emphasized many times, once I choose a basis for a vector space, I can move freely between matrices and linear maps. Okay. So we are doing exactly the same thing as we did for Rn. Namely, we take the linear map, take the matrix, take the transpose of the matrix, and then take the linear map corresponding to that linear map. Now, this I could have done with respect to any basis, but this equation will hold. See, this equation, which refers to the inner product, will hold only if you choose an orthonormal basis. So, and this is something that again, you know, if you check and do the arithmetic, it will just fall out. There is no mystery to, you will not have to do any, you know, it will automatically, you will get the result that you want, but you have to do, you know, do the checking. Okay, so to summarize, we have defined for a real inner product space the notion of an adjoint of a linear map. To every linear map, you associate another linear map, call its adjoint. It's defined using the data of the inner product. This is linear in the sense that if you take two linear maps A and B, the adjoint of A plus B is the sum of is A adjoint plus B adjoint. If I take A and multiply it by a scalar lambda, the adjoint of lambda times A is lambda times the adjoint of A. So it's this associate, and if I take the adjoint twice, I get back the original linear map. Okay, so now comes a very important definition, the notion of a self-adjoint linear map. So definition, let V be an inner product space a linear map A dagger V to V is self-adjoint if, well, guess what it should be. For every A, I have defined its adjoint, A hat, I defined its adjoint A hat dagger. So what is the natural notion of a linear map being self-adjoint?
It itself is its.
Yeah, if A hat dagger is A hat.
Sir.
Yes.
Sir, from the previous corollaries, what we are seeing that given a linear map A hat corresponding to an inner product space, the transpose of it is a potential adjoint of the linear map, right?
Yes, yes.
And by the uniqueness we have that the transpose is the only such adjoint.
Yes, yes.
Oh, so if it is self-adjoint, then the transpose of it is basically equal to.
Yeah. So the self-adjoint linear maps are those such that the matrix of the linear map is symmetric, provided you express the matrix in terms of an orthonormal basis.
Oh, okay, sir.
Okay. Yeah. So to summarize the previous discussion, and this is an easy exercise. Linear map A hat V to V with V, of course, always an inner product space. Is self-adjoint if and only if the matrix representing A, the matrix A representing A hat is symmetric. Now, as written, this doesn't make sense because the matrix A representing A hat, I should add a qualification because the matrix depends on a choice of basis. So I cannot allow arbitrary basis. Yeah. with respect to 1 and therefore any orthonormal basis. So in other words, if I take a linear map, I want to check if it's if it's self-adjoint, take any orthonormal basis, look at the corresponding matrix. If it's symmetric, then I can certify this linear map is self-adjoint. Then if I choose any other orthonormal basis, I'm guaranteed that the matrix corresponding to that will also be symmetric. Yeah. So maybe I misspoke. Let me repeat. I'm given a linear map V to V. I want to certify if it's self-adjoint or not. Take any orthonormal basis, express the linear map as a matrix, check if that matrix is symmetric. If it's symmetric, I can certify this linear map is self-adjoint. And then you are guaranteed that if I had chosen some other orthonormal basis, the matrix corresponding to A hat with respect to that second orthonormal basis, which in general will be another matrix, but it will also be symmetric. Very good. So now we come to the major theorem of linear algebra, one of the most important theorems. Actually, the really crucial, this theorem in its natural form comes up when you consider complex vector spaces with Hermitian inner products, which we don't have time to deal with. But the spirit of the theorem is not just spirit. All the ideas are here already in the real inner products situation. So you're not missing too much. Okay. So here is the major theorem. Let A hat V to B be a self-adjoint linear map. V is n-dimensional inner product space. Then there exists an orthonormal basis of V consisting of eigenvectors of A hat. So in fact, let me be more explicit. Then all roots of the characteristic polynomial are real, and there exists a basis, an orthonormal basis of V consisting of eigenvectors of A hat. Explicitly, there exists U1, Un vectors in V such that Ui inner product Uj is delta Ij. That means it's an orthonormal basis. And A hat Ui is lambda I Ui, lambda I real numbers. Now, note lambda 1, lambda n need not be distinct. I'm not claiming that the roots of the characteristic polynomial are n distinct real numbers, but characteristic polynomial will have n real roots counted possibly with multiplicity. Okay, so some roots, so the characteristic polynomial will factor into into so P A hat T will be of the form T minus lambda I pi I equal to 1 to n, where the lambda 1 to lambda n are real numbers, not necessarily distinct. So that is this is called the spectral theorem for self-adjoint linear maps. Spectral theorem. The set lambda 1 lambda n is called the spectrum of A hat. Hence the word, hence the term spectral theorem. Okay, so now I'm going to begin the proof of this theorem. But before that, any questions?
Sir,
Yeah.
this is not exactly related to what we're doing today. It's just a general question. So in the notes, I was going through your notes very thoroughly. And I think there was this whole section on generalized eigenspace decomposition.
Which I'm skipping over. Yeah. So yeah.
Oh, okay.
Yeah.
So sir,
I'm
will
skipping
that
over
be
in the course, but I'm happy to answer questions. So maybe, so this is a general remark to everyone. So there is, so that section on generalized eigenspaces, I'm mostly skipping over. Some of it, material in that section, I put in this exercise that in the assignment that I posted. But if any of you, I mean, in fact, I strongly encourage everybody to read as much of the notes as you can, even if it's not, if I tell you explicitly that we won't have to deal with it in the exams. And now or in the future, if you write to me with doubts about anything in the notes or corrections, such things are very welcome. So I'd be happy to engage with you in these matters, for that matter, anything else. So, so this was Rajdeep Ghosh, right?
yes, sir. So
So
no,
if you are reading that, and if you have questions, and for that matter, anybody else about the generalized eigenspace decomposition, please feel free to write to me.
yes, sir. I just wanted to ask whether the portions that are in the notes, but the ones that you don't cover in class, are like those won't come in the end. Right?
No. That is the thing. So, so I have said explicitly that this chapter on, I think it's I've given it some strange title, desperately seeking eigenvalues.
Yes. Sir.
So that chapter is not covered in the exams, except I've extracted some small part of it and put it into assignment 3.
Okay.
That assignment 3, I expect you to study very carefully. If I remember right, assignment 3 comes from the first 2 subsections of that chapter. So am I clear about that chapter? Hello? Did I lose everyone?
Yes, sir. Sir,
yeah.
It's clear.
Yeah. Okay. So now back to the spectral theorem. Everybody has had time to stare at it. Can I go ahead and begin the proof? The proof will involve several steps and very, very important ideas in linear algebra. So I expect you to follow the proof carefully and be able to answer questions about it. Okay. Understanding this proof is extremely important. Sometimes proofs are, just legal documents, but this is a this proof is full of ideas and techniques that you need to. So in other words, you need to understand the proof, internalize the proof, and I cannot really emphasize how useful it will be to be able to understand the proof well. It will give you a lot of geometric intuition about linear algebra. Okay. Okay, so let us begin the proof. Okay, so the first thing is to prove this, what I stated about the characteristic polynomial. So recall that if I have a n-dimensional vector space and a linear map acting on that vector space, the characteristic polynomial will have some number of real roots and some number of complex roots with non-zero imaginary parts, which will come in pairs. And it's only the real roots that actually correspond to eigenvalues, and because those eigenvectors will only exist for those guys. Okay, but now what I'm saying is that if you have self-adjoint linear map from V to V with V an inner product space, then in fact it doesn't have any, the characteristic polynomial does not have any roots with non-zero imaginary part. Okay, so let's prove that. Okay, so proof comes in steps. Proof of the above spectral theorem comes in steps. Step 1, if A is self-adjoint, it has no then and lambda is the root of PA hat, then lambda is real. So it doesn't have any roots. The characteristic polynomial doesn't have any roots with the non-zero imaginary part. Okay. So again, this is a case when I am forced to use matrices because of shortage of time. Okay. So this is proof of step 1. Proof. Yeah. Is there a question? Hello. Was there a question? No. So choose an orthonormal basis and let A be the corresponding matrix. Yeah. By what we have, by assumption, since A hat is self-adjoint, since A hat is self-adjoint, A is symmetric. Now let lambda be a root of PA hat equals PA. Remember, the characteristic polynomial of a linear map is, all by definition or whatever, is really the characteristic polynomial of the corresponding matrix with respect to any basis. Here, you don't need the basis to be orthonormal. So lambda is the root of the characteristic polynomial of A, but lambda could have a non-zero imaginary part. We want to rule out the possibility that lambda has a non-zero real imaginary part. But think of A as defining a map Cn to Cn. Okay. By V going to A, V. So this is a column vector of complex numbers. This is matrix multiplication. So even though my original linear map A hat was working from real vector space to itself, once I have a matrix, n by n matrix, I can choose to think of the matrix as defining a linear map from Cn to Cn. Now, if lambda is a root of PA, the kernel of the map lambda ICN to A, Cn to Cn is non-zero. So there exists a complex vector. So let me call this lambda 0, by the way. V0, which is a non-zero vector, such that A V0 is lambda 0 V0. So let me write this out. This means Aij Vj sum over j is lambda 0 Vi. Okay. So V1 to V, so I should put a 0 here. 0 here. V01, V0n. So I'm sorry for this 0 business. I think that's, let me not put, I don't think I need a 0 here. So these are complex numbers. So I have this n, these are n equations here. Okay. So I equal to 1 to n. These are n equations. Both sides are complex numbers. So now let's take the complex conjugate of both sides. Taking complex conjugation, sum of complex numbers, conjugation of sum of complex numbers is the sum of conjugates, and the aij's are real numbers, so the conjugates are the same. So you get equal to lambda 0 bar Vi bar. Taking complex conjugates. Now multiply, so this is true for I equal to 1 to n. Multiply the ith equation by Vi, I'll get sigma j Aij Vi Vj bar is lambda 0 Vi bar. Now sum over I get lambda, this becomes lambda 0 sum over I Vi bar. Now since the Vi's are together, this is a non-zero vector. This is non-zero. In fact, this is a positive real number. This is a positive real number. On the other hand, this is equal to, so I now I've summed over I. So the left-hand side is sum over I, sum over j, Aij, Vi, Vj bar. So this is, I interchange the sums.
we are also taking the complex conjugate of lambda naught, right?
Yes, thank you. Thank you very much. Okay. But this is equal to sum over j equal to 1 to n vj bar. Now remember, A is symmetric. So this is A ji vi I equal to 1 to n. But this is lambda 0 vj. So we get this becomes lambda 0 sigma vj bar. So this is equal to lambda 0 bar sigma vj bar. Now this is a real number greater than 0. This is really the same real number greater than 0. So lambda 0 equal to lambda 0 bar. So we have shown that if I have a real inner product space and a self-adjoint linear map that acts from V to V, then any root of the characteristic polynomial must be real. So we have proved part of our claim that the characteristic polynomial factors into products of linear terms, real linear polynomials. Okay, we have proved this fact.
Sir, could you scroll down to the last question?
Yeah. Here, is it okay? Here.
Yes, sir. Yes, sir.
Yeah, I'm going to leave you and take a little break. So can I leave you here? Yeah, I'll be back
Yes,
in
sir.
3 minutes. Yeah, I'm back. Can I go ahead? Or do you want to ask something? Somebody who asked me to scroll down?
Sir, it was me.
Can I go ahead?
Yes, sir.
Okay. So now step 2 is inductive. Yeah, Rishabh, yes.
So can you go over the last part a little bit? Like after summing over I.
Here. You
Yes.
mean here? You got?
Yeah, sir. You've written sum over I after that.
Yeah. So you mean this part?
Yes, sir.
So are you okay with this equality? So what I'm doing is I'm taking this equation. So I have these n equations here. I equal to 1 to n. Okay.
Yes, sir.
Hello.
Yes, sir.
See, this, sorry, I think that this should not be here. This is here V is a vector. So this here V is a vector. Okay. Now, so this is an equation between vectors. You take the vector V, multiply it by the matrix A, and that is lambda 0 times V. That is what this says. But now you write out the components of this equation, then you get these n equations here of real numbers, of complex numbers. Rishabh, you're the one who asked this, right?
Yes, sir. I'm okay with this.
You're okay with this. Okay. You take complex conjugate of this equation, you get this. So there are n equations here. I equal to 1 to n. You're okay with that?
Yes, sir.
Multiply this equation, the ith equation by Vi. I get this.
Yeah, okay.
Okay. Then sum over I. So I get n equations. For every I get this equation, sum over I. The right hand side, I get this. The left hand side, I get this double sum over I, sum over j, because this is a single sum, and then I am summing over I. Okay,
Yeah.
Rishabh?
Yeah. Yes, sir.
Yeah. So now I write this sum as a, so here I'm first summing over j and then summing over I. I reverse that. First sum over j and then sum over I. Sorry, I first sum over I and then sum over j. So that's what I'm going from here to here. I'm just reversing the order of summation. Are you okay?
Yes, sir. Yeah.
Okay. Then I don't do anything out here, but then I look at this part. Okay. And I use the fact that A is symmetric to write, instead of Aij, I write Aji.
Okay. Yeah.
Now I recognize this as the matrix A multiplying the column vector B and the jth component of that. So that should be lambda 0 Vj.
Okay. Yeah. Got it, sir.
Okay. So then I have this. So you have, I get lambda 0 is lambda 0 bar, because on both sides, this is a non-zero, in fact, positive real number. Because remember, I'm taking an eigenvector corresponding to the possibly complex lambda 0. But an eigenvector by definition is non-zero vector. So these VIs, which are complex numbers, cannot all be 0. Therefore, among the VIs, there must be at least one non-zero VI. So that will contribute a non-zero real number. But each of these is a positive, non-negative real number. So the sum must be non-negative and positive.
Yes, sir. I got it now.
Okay.
Thank you.
Okay.
Sir, at the very beginning, you considered lambda 0 to be the root of PA, right?
Yeah. So the point is, if I am looking at a linear map from a real vector space to itself, a root of if I have a root of the characteristic polynomial, if it's not real, the root is not real, there will not be a eigenvector corresponding to that, real eigenvector. But if I'm looking at a complex vector space, then for every, even if I don't care if the root is real or complex, for any root, the corresponding, there is an eigenvector. That's what I'm using.
Okay, sir.
Yeah. Okay. So the next step, I think I should just stop with that, because this is fairly dense. Unless you guys go back and read the notes and put in some work, you are going to not understand this, and you're going to miss out on possibly the most important part of the course. Okay, so I cannot emphasize how important it is that you do your homework regarding this proof. So step 2. So we have shown that given any self-adjoint linear map V to V, it has n, the characteristic polynomial has n real roots. So it has, for step 2, I don't need the full strength of that. All I need to know is that it has at least one real eigenvalue. Okay, so A hat has at least one real. By an eigenvalue, I only mean in the corresponding field, which is real now. Okay, lambda. Okay, so let me call that lambda. Okay, so let U lambda be a corresponding eigenvector. By dividing by norm U lambda, I can assume this is unit length. I can assume U lambda is 1. So let me put an arrow. Yeah, it's of unit length. Okay, so this is the situation. With all this work, what we have shown is that see, with a non-symmetric linear map from a vector space to itself, real vector, you know that it could happen that it has no eigenvectors at all. For example, the rotation in the plane. But what we have just shown is that if I have a symmetric linear map, it must have at least one, the characteristic polynomial has at least one root, one real root. So there is an eigenvector. So in fact, we will go further, but the starting point for the next step is that if there exists at least one eigenvector. Now comes the crucial step, step 2. Let V prime lambda, so let me call this U hat 1, sorry. And this is lambda 1, this is U hat 1. Be the orthogonal complement of the one-dimensional space spanned by U hat 1. So in other words, i.e. V prime 1 is V in V, so that V inner product U hat 1 is 0. Then claim A hat leaves V prime 1 invariant and A hat restricted to V prime 1 is self-adjoint. Okay, we are, so this is a good point to, so now I will leave, I'm going to, for the moment, I'm going to just leave the rest of the proof as an exercise. I will come back and finish the proof on, yeah, we will almost definitely have a class on Friday. So we'll finish this on Friday. Exercise, prove the claim, and then finish the proof by induction on n equal to dim v. So Well, the induction is clear. Once you prove that A hat leaves the orthogonal complement of U1 invariant, and that it's easy to check that then the restriction of A hat to this orthogonal complement is a self-adjoint linear map. But what's the dimension of V1 prime?
1 less than V.
Yeah, it is n minus 1. So so now you have a self-adjoint linear map on a n minus 1 dimensional real inner product space. So by induction, you can assume that there is an orthonormal basis of eigenvectors U1, U2 to UN for V1 prime, and then add on U1 to this whole bunch, and you would have got the proof of the claim. Okay, so and checking that A hat leaves V1 prime invariant is really trivial. You have to use the fact that A hat is self-adjoint. So I'm going to leave this as an exercise. But you see, some of you might have wondered why it is that even though I'm forced to use matrix arguments in between, I didn't choose to go the whole hog with matrices. You know, why did I have to formulate the theorem in terms of linear maps rather than matrices? Well, this is precisely the reason. Even if you started with the n by n symmetric matrix and wanted to prove the spectral theorem for that matrix, then I would have the inductive proof would have taken me to the orthogonal complement of one eigenvector of that matrix, and the orthogonal complement of even if you are in Rn, if you choose some arbitrary unit vector and take its orthogonal complement, that orthogonal complement doesn't come with a natural orthonormal basis, unless you happen to be lucky and your unit vector was the unit vector along one of the axes, which need not be the case. Okay, so the natural way of proving this theorem proceeds via abstract linear maps, even if you only want to prove the theorem for matrices. And in fact, the really natural proof would avoid that step where I went through matrices to prove that any root has to be real. Okay, but unfortunately, we have not, because I am not talked about many things. In fact, even when I taught the course last time, I had to do this artificial step. Very good. Let me now